Okay, everybody, thank you for coming to this session on the kernel report. Can you please welcome Jonathan Corbett?
All right, well, thanks, everybody. Good to be back in New Zealand. I'm John. I'm here to talk about the kernel. I'll start, as I often do, with a table of what we've done over the last year. 4.15 came out just after the close of LCA last year. As you can see, we've done another 5 releases since then, so 6 over the course of the last year. They're all major releases with lots of interesting stuff, 13,000 or so change sets in each containing the work of 1,700 or so developers, each coming out in 9 or 10 weeks. Or if you add it all up, you get something on the order of 83,000 changes merged into the kernel over the course of the last year, coming from over 4,400 developers. All big numbers, a whole lot of stuff, but the truth of the matter is, I've been putting up these tables for years. And this is just what it looks like anymore. At this level, at least, the kernel development machine is pretty well tuned, runs pretty smoothly. You know what it's going to do. So I can put something up like this, but it's kind of like putting up a chart of sunrise times. It's, it's potentially useful, but you're not really going to be surprised by it. So that said, there's one number that jumps out here, which is that 4.15 took 77 days, 11 weeks to produce. This is the first time we've taken more than 10 weeks to put out a kernel since 3.1 came out in 2011. 3.1 was delayed by the compromise of kernel.org, and we had to rebuild all of our infrastructure and all that. So, one might imagine that something similar happened here to slow us down. And no, it's not that this guy went diving, not this time. It's our good friend's Meltdown Inspector that slowed down that particular kernel release. So I'm not going to talk much about the vulnerabilities themselves. They've been well described elsewhere in a lot of ways. But I want to talk a little bit about how the interaction of these vulnerabilities in our community work, because there's some interesting lessons to be learned from this. I've been assured by people at Intel and such that this is a brand new class of security vulnerability that nobody ever thought of before. Brings a whole lot of new stuff, but from the point of view of the kernel community, they really look a lot like software vulnerabilities. We've got something that's broken, we need to fix it. So we need to gather together the people in our community with the requisite expertise, get them working on it, create some fixes, and get them out to our users. Now it happens that we have a process for doing this. It runs pretty smoothly. It handles, I'm told, about 1 vulnerability per week. And most of the time, we don't really even know that this is going on. But this process wasn't followed for Meltdown Inspector at all. It was totally ignored. What we got instead was a whole lot of secrecy. Meltdown Inspector first started being discovered in June-ish of last year. The kernel community was informed at the end of October. Right? Yeah, you're right. Okay. Very good, 2017. So you understand. We were not informed until several months later. Okay, I can get the relative times right. So that's a long time for this stuff to be festering without giving us a chance to do anything about it. Once we were told, there was an awful lot of siloing that went on, where certain groups were given information about the vulnerabilities, but they were not allowed to talk to the other groups that were also working on these vulnerabilities. So our normal community dynamics couldn't happen. The developers couldn't talk to each other. They were forbidden to do so. And so you saw this, for example, when the disclosure happened, and each distributor shipped a different set of fixes because they had all had to pretty much develop these in isolation. And there are a lot of consequences to this, but it's interesting because there was a natural experiment that was performed here that shows just what the consequences can be. If you look at how Meltdown was handled, the fixes for Meltdown, in particular the kernel page table isolation patches, were developed in public, even though the vulnerabilities were not public, at least for a while. The fixes were. And what we got as a result of that were a lot of developers coming in and working to make kernel page table isolation work better. These patches changed a lot over the course of the time they were worked on before the disclosure happened. They were improved by people who had no idea what the patches were actually fixing. But they made them better anyway. And the result was that by the time the vulnerability, the meltdown vulnerability was disclosed, these patches were pretty much ready. They were in the main line. There were a few bugs, but that's normal. And what was then shipped by distributors was pretty much uniform and is more or less what we still have now, right? The community was able to do its thing and come up with a good set of fixes there. Spectre was much more secretive, where a lot of the work was, again, done in private and with little communication even among the people who were working on it. These fixes were not at all ready at the time of disclosure. Each distributor shipped something pretty much different, and regardless of what they shipped, that's not what made it into the main line, because as soon as these patches got out into the open and people looked at them, they kind of said, ooh, and things got reworked quite significantly. So what went into the main line was very different from what anybody shipped. So a whole lot of stuff had to be redone. As soon as you take away the ability for people to work together, even in a private, non-disclosure sort of setting, you really take away a lot of the magic that makes our community work as well as it does. And we saw it very well here. And the consequences have been with us for quite a while. We had some interesting issues with regressions back in, performance regressions back in November, resulting from the use of an Intel instruction, or an Intel operating mode really, that didn't work quite the way that we thought that it might be. And what it comes down to, as Paolo said at the time, is this is really still an afterthought, a shadow of the secrecy that surrounded all of this stuff back 1 year before. So this costs us a lot. It did not work well, and it did not help our response to these problems. So there's some good news, which is that a lot of these lessons seemingly have been learned. Everything I've been told says that the handling of the L1 terminal fault vulnerabilities, which were disclosed in August, was much better than that. And there seem to be signs that the vendor community is beginning to understand how we have to work with all this. And a key part of the understanding here is that the kernel project really is a single engineering organization in an awful lot of ways. We represent a lot of companies, work in a lot of different circles towards a lot of different ends, but when it comes to working on the kernel, we work together and we work as a group, and we work across whatever boundaries may separate us in other aspects of our lives. So if you're going to present us with a big problem, you need to present it to the engineering organization, not to some little piece of it. But where we really ran into trouble with things like Meltdown and Spectre is that the kernel project may be a single organization, but it is not one that can sign non-disclosure agreements, right? We can't sign this thing that says if we disclose this stuff, we're gonna, I don't know, give up our firstborn children or whatever. And more to the point, even if we were, there are quite a few people in our community who would simply refuse to do that. We have a lot of developers who don't want to sign non-disclosure agreements for all kinds of reasons. They really run counter to the openness in which we want to work. So as this guy over here put it a little while back, his way of dealing with this is to have a gentleman's agreement with the vendors where they come to understand that the leaks don't come from him. And once they learn to trust that, this agreement can hold. So that really shows the way forward that we're trying to pursue in the community here, which starts by showing that we can be trusted with this kind of information in a closed setting. And I think that we have done this pretty well over the years. We aren't all that leaky most of the time. Establishing well-known contact points so that when some hardware vendor has to say, well, excuse me, but we got a little problem here, they have somebody to talk to who knows how to handle this. And then we need to actually document all of this stuff. And that document is, I'm told, they promise, being written right now, and will hopefully come through. Then we have to get it through the documentation maintainer. It's a real pain in the butt. But eventually we'll have all this stuff in here, and we'll have a better procedure. And hopefully we'll never see anything quite as bad as what Meltdown and Spectre were again. But then I'm known to be an optimist. So other stuff, just while I'm on the area of Meltdown and Spectre, there's a lot of work going on to find and fix speculative execution gadgets. They're not easy to find. And so that'll go on for a while. A lot of work to try to claw back some of the performance that we lost when we fixed Meltdown and Spectre. So we're seeing, for example, a lot of patches right now working on indirect branches and trying to find ways to avoid doing indirect branches, because those are now very expensive things to do. Because you have to use this whole ret pooling mechanism to prevent the processor from speculating the wrong way and all that sort of stuff. So there's a lot of fairly tricky coding going on, trying to make things go faster again in that area. And you're seeing things like what's called co-scheduling, which is a proposed mechanism for the CPU scheduler to allow a system administrator to say, these groups of processes trust each other. They can be running on the same CPU at the same time. These other ones, no, they cannot share it at the same time. We have, over the years, perhaps allowed a little bit too close sharing of resources in the quest for performance. And this is beginning to hurt us in a number of ways at all levels, from the processor stuff to the stuff that's going on now, trying to avoid disclosure of information through sharing of the page cache at the kernel level, and so on. Beginning to realize we maybe can't be quite that close between processes or users running in different security domains. So there's going to be a lot of work, I think, done there to try to separate things out that way and do it in a way that doesn't cost us all the performance that we got by bringing in all that sharing in the first place. And then, of course, there's the final aspect of this, which is that we got to get users onto current kernels. Because if you're not running something fairly current, you probably have much worse problems than Meltdown and Spectre anyway. And there's an awful lot of people running some pretty ancient kernels out there. And that leads to the next thing that I wanted to talk about, which is the stable kernel process and what we're doing there. Most of us, of course, are not running mainline kernels on our devices. We're running something that was put out by the stable team, which is another term for Greg Crow-Hartman. He's been busy and so on. This is the state of stable kernels, or at least it was the state a few weeks ago when I wrote this slide. It's a little bit obsolete now. But you get the idea, right? There are several kernels under maintenance right now, dating back as far as 2014. They get a lot of fixes, right? 4.9 has gotten, at this point, I think over 11,000 fixes put in there. That's an awful lot of fixes going in there. It's a lot of stuff that you want to have in a kernel that you're counting on to keep your system stable and solid and secure. For the most part, this works pretty well. We're cranking these out, but there's always things that we can work on here. One of the changes that we're seeing is an increase in the support periods for these kernels. The rules for some years were that the long-term support stable kernels, of which is about 1 per year, would be supported for a period of 2 years. It turns out that 2 years is about what it takes for a released kernel to go through everything that, say, a mobile device manufacturer has to do to it and get it into the hands of a user. It takes about 2 years to do that. So about the time these kernels are actually being deployed and used, the support goes away. And that's not perhaps ideal. So Greg has said he'll support 4.4 till 2022 now, 4.9 till 2023. That's 6 years of support, which is going to be a whole lot more useful and that sort of thing. And is definitely a nice thing for him to be doing. Help to encourage the use of these kernels. There are other projects like the Civil Infrastructure Platform that's looking at supporting kernels for 10 to 20 years, which is insane. But if you think about systems that are, say, deployed into buildings, like the HVAC system that's keeping this room so nice and fresh for us, you know, or systems in elevators or in cars or whatever, right? They're expected to work for a long time. And so if we can actually support them and keep them secure over that time, that is a good thing as well. This is not going to be an easy thing to do. I wish them luck with it. We're always trying to get more fixes into the stable kernels. As I said, the 4.9 series has seen 11,000 some fixes go into it, but during that same period of time, the mainline kernels had over 160,000 changes going in there. There's a pretty good chance that among those other 150,000 changes that went into the mainline, there's a few fixes that we probably wish had gone into 4.9 as well. So we look harder to find fixes, improve our discipline there. There are even people like Sasha Levin who has put together a machine learning system that tries to automatically identify patches that look like fixes and kick them out for review and put them in there. And so we're likely to see the volumes of changes going into the stable kernels increase even further, which is in general a good thing, but that leads to one of our constant arguments in the in the development community, which is regressions in stable kernels, because users have this really unreasonable expectations that stable kernels might be stable. And so if they break, this is not a good thing. So 4.18 saw a performance regression that actually was never fixed before 4.18 went out of support. 4.19 got a regression that corrupted file systems. It was there for several 4.19 stable releases before it was found and fixed. That's the sort of thing that the users tend to get really grumpy about, and it tends to put them off from updating their kernels and getting the new stuff that we want. So you really don't want to have that happen. Now, if you're going to be incorporating thousands of changes into a stable kernel, you're going to have regressions. I don't see any way that you can fix that, but we can try to do better. But it's not always clear how you can do that other than to test more, to review more, and try to do a better job as much as you can. The other issue with stable kernels is these huge and invasive fixes, right? Kernel page table isolation was thousands of lines of tricky code at the most fundamental levels of our memory management in system call entry code and all of that. This is not a small change. This is not the 100 lines or less fixes that the stable rules say are eligible for stable kernels, right? So if you're going to take a fix like that and backport it to a recent stable kernel, this is hard because other things will have changed and they aren't all necessarily just flagged as, oh, this is a change that's going to break your kernel page table isolation when you backport it. So it's a tricky task. And if you're trying to backport further to really old kernels, it becomes almost impossible to do this in a way that isn't going to introduce regressions and problems like that. And you see this in, for example, the fact that the 4.4 kernels still don't have all of the Spectre fixes, because it's too much work to do it, and you can't pay people enough to actually try to do this work and stay sane. So this leads to questions that people ask about whether this whole model of keeping really old kernels on life support for years and years is really the right model that we should be doing at all, or if we should be doing something a little bit different. People have been questioning this for years, but the voices seem to be getting louder over time. You just realize that you can keep a kernel with a number like 4.4 on it, and it still says it's a 4.4 kernel, but it's had 10,000 changes applied to it. It's pretty far removed from what was 4.4. And at this point, is that really going to be more stable than something more current? Right? And it's not an easy question to answer. But the solution that a lot of people are pushing towards is to try to encourage people to upgrade to more current kernels, like the current long-term stable release. Because that is the kernel that has all the latest fixes that we may be able to identify, and a lot of useful features as well, including things like security features that you might actually want to have that would not ordinarily be backported further than that. They are honestly the best kernels that we know how to make at this time. So this is a really hard sell to tell, say, a handset manufacturer, you shouldn't just send out some patches, you should be updating them to a current stable kernel. It's an almost impossible sell. But it's a line that we keep hearing, and at some point, maybe, we will start seeing some progress along these lines, because I think this is something closer to the real solution for how we keep our systems secure and stable and running in the long term. That leaves you with one little remaining problem, which is that if we're going to tell people you should run a current kernel on your 20-year-old hardware, we need to make sure that we didn't actually break that 20-year-old hardware in the process. And that is very hard to do when none of the developers working on the kernel have that hardware and can test it now. So it's a problem with stable backports as well, but it's even worse with current kernels. And we don't really have good fixes for that other than, say, more testing. So I'm not going to talk too much about testing, but it's worth mentioning just because for such a long time, we had no real convincing story on testing at all in the kernel community. In fact, it was said, not really totally in jest, that that was what we kept users around, was to test our releases. And there was some truth to that. And honestly, there's always going to be some truth to that because no kernel developer can ever have all of the hardware or all of the workloads or all of the combinations of hardware and workloads that exist out there. So there are always going to be surprises when you make kernel releases. But that said, you can do better than we have done over the years. And the good news is that we are actually doing better than we had in past years. There's systems like the zero-day robot, which will pick up patches off the mailing list and do build and boot tests. And then you get this cheery little note that says, I love your patch, it's great, but actually, no, it's not so great. Kernel CI is a distributed project doing a lot of testing, mostly on embedded hardware. K-self-test, set of tests built into the kernel itself. Syzbot is a fuzz testing system out there that produces a whole bunch of reports of its own. Linux kernel functional testing out of Linaro. The Linux test project has been there for many years doing testing at the system call level. I just saw a talk a couple days ago about a thing called Snowpatch, which is trying to create another nice continuous integration system for the Linux kernel without messing up our workflows. And there's a whole lot of work being done within vendors. For example, Google does a bunch of tests on RC kernels to make sure that it's not going to break Android, that sort of stuff. So there's stuff happening here. This is a long, long way from being a comprehensive test suite for the kernel. We have quite a long road that we have to follow yet, but you have to start somewhere. And I think the good news is that we have started, and there's quite a bit of work that is being done in this area at this point. I would say that if there are people out there who would like to contribute to the kernel and don't necessarily want to do kernel development, that improving our testing is really something that would be beneficial to an awful lot of people. So it's good to see work that is being done in that area. So enough of that. Let's talk about crazy stuff for a moment. Because this is an area that I think people don't fully appreciate some of the interesting things that are going on here. BPF, originally called the Berkeley Packet Filter, is an in-kernel virtual machine. It's essentially an emulated computer built into the kernel. It allows the upload of code, binary code written for this virtual computer into the kernel to run in the context of the kernel. This can come from user space. It can come in some settings from unprivileged processes in user space and run in the kernel. And so one might think that's a bit of a scary thing to do. And it is, but BPF does come with a built-in verifier. So a whole system that runs a static analysis of any program that has been fed to it and does a bunch of simulated execution to make sure, for example, that the program cannot access any memory that it should not have access to make sure that it terminates and won't lock the kernel in an infinite loop, to make sure that it does not leak data out to user space. There's a whole lot of tests that are done there. So since we know that this kind of code is always bug-free, we know that any BPF program is going to be safe to run in the kernel. It also has an in-kernel just-in-time compiler. We have a just-in-time compiler built in to our kernel that will compile these programs, which are again written for an abstract machine, down to the current hardware that you're actually running on, which makes them fast. And this is a good thing because BPF programs are showing up in all kinds of places. You see them being used for security policy decisions, for example. The secure computing mechanism has allowed the attachment of BPF programs to system calls for some years now. The landlocked security module, which is still out of tree but is likely to come in, will expand that capability quite a bit and allow processes to sandbox themselves by attaching programs to system calls to make policy decisions whenever the process tries to do something. Protocol implementations. If you've got an infrared remote control, that one is going to speak a different protocol than any other infrared remote control out there because after all, our play button has got to be different than everybody else's play button. And we couldn't possibly have a common protocol for this sort of thing. So you can put 100 different protocols for infrared receivers into the kernel, and we have done that sort of thing. But we also now have a mechanism where you just load a little BPF program that understands your specific infrared controller. And it all works. You don't have to carry all this code in the kernel. You can make an old kernel support a new controller just by loading a little program into it, not having to build a new kernel or even build a kernel module for it, and so on. It adds a lot of flexibility there while shrinking down the stuff that you have to carry in the kernel itself. Kernel instrumentation, tracing, all that has made heavy use of BPF for some time now. If you haven't looked at what's being done at the BPF compiler collection and all that, and some of the tools that are out there, you really should, because there's a lot of stuff out there, a lot of tools for seeing what's going on inside a kernel, for tracking down problems, for debugging things, for finding performance issues, and so on. There's a lot that's happening with this sort of stuff. And you see it, for example, in packet filtering, which is unsurprising because we are talking about the Berkeley packet filter. But BP filter actually does things at a different level. Rather than supplement the existing firewalling mechanism, it essentially pushes it aside. And you no longer write IP tables, rules, all that. You simply load a BPF program that will inspect packets and apply whatever policy you can code into BPF and filter packets in that regard. So it gives you a lot more flexibility in that sense. You don't have to do something that some NetFilter developer might have envisioned you might want to do. You can code pretty much anything you want. The interesting thing is that this really has the potential to be faster, because rather than having this whole filtering mechanism that can do anything that you might want to do, you have a very focused little program that does exactly the filtering that you want to do and nothing else. So BP filter is new. It's only been in for a couple releases, maybe 3 releases at this point. It's not really ready for primetime use, but I expect it to come around, and it may eventually push aside our existing firewalling mechanism. We will see about that, but I think the potential is there for that to happen. Finally, there's a thing called the Express Data Path, or XDP. It's an effort within the networking community to win back some of the users who have moved to user space networking stacks over the year in the efforts to get higher performance for very specific sorts of applications. A FXDP is a particular operating mode wherein most of the packet processing is pushed out of the kernel into user space. The kernel will receive packets from the network and stick them into one of a series of shared memory ring buffers, and then user space consumes the packets out of these buffers without ever having to call into the kernel at all. So no system calls, it all happens very quickly, and then user space can do whatever special thing it needs to do with those packets. But the sorting of these packets into the ring buffers is done with a BPF program. That's a vital component to supply the kernel side piece of this problem so that you can do your fast data processing this way. There are other places that's showing up as well, but I think you get the idea. And we're seeing 2 sorts of uses of BPF here. One being to supplement the existing functionality that's in the kernel by adding the ability to do policy decisions or whatever, but also to completely replace it at times, to just push aside something that was done in the kernel and supply your own version of it instead, which is a pretty fundamental change to all that. It allows us to push this code into the kernel in a couple of different ways. But the story doesn't actually stop there, because we're seeing an equal amount of work, it seems, to push code in the other direction. So again, AFXDP pushes the actual processing of network packets out of the kernel and into user space. The secure computing mechanism just gained with 5.0 the ability to push policy decisions back out to user space. So even though the system call filtering is being done in the kernel, it can call back out to user space to make the decision about whether a particular system call should proceed or not. ELF modules are this crazy mechanism that came with BP filter that allows the incorporation of essentially a user space program into the kernel, and it runs as a special thread within the kernel in user space, so that certain kinds of complex processing can be done in a more isolated manner where you don't necessarily trust it to be well enough debugged to really be solid, stable kernel code or something like that. You want to keep it separate, right? Put a security boundary there. User fault FD is a system call we've had for years, actually, that allows the pushing of page fault handling, which is something you might think of as a consummate kernel task. Very low-level memory management stuff. You push that out to user space instead and make your decisions there. And all of this is kind of changing our view of how our systems work. If you think to the picture of a Unix system built around a monolithic kernel, you've got this hard, well-defined kernel in the middle of things with firm boundaries around it and very narrow interfaces to the user space that surrounds it. All of this stuff moving code in both directions is making this boundary a whole lot more porous. And it's making our kernels a lot more amorphous. as code can be moved to either side of that boundary depending on what the workload and the mood of the system administrator calls for. So there are people who say that what this really means is that Tannenbaum was right all along, and that we finally figured out that we need to move to a microkernel architecture. Other people see it differently. But the truth of the matter is that the changes, the shape of our system is changing, and it's going to be interesting to watch over the coming years to see just where this takes us and how we put our systems together in the coming years as these technologies continue to grow and mature. All right, so this is something I've talked about before. I have a bit of a different take this time because there's some interesting stuff that I've stumbled across in the meantime. So how many of you have a phone that runs Linux? Raise your hands. So many of you have seen this before. I stole this slide from Tim Bird years ago. I need to get a new one from him. This is just a listing of some popular handsets and the number of lines of out-of-tree code that are shipped with those handsets. And if you look at it, you see numbers heading up towards about 3 million lines of code added to the kernel before it is shipped in one of these devices. Now, if you think of the kernel as being currently 24 million-ish lines of code, you can figure out everything you don't need in a handset, which is certainly most of it. Right, you get down to a few million lines of code in the kernel that you're actually building for these devices. Then you add 3 million lines of your own code. What you have is something that's pretty far removed from anything we actually call a Linux kernel. And this isn't just adding device drivers and so on. A lot of these handsets, for example, replace the CPU scheduler, which is, this is a pretty fundamental change. And so, is your phone really running Linux? Well, it will identify itself as such. But again, it's pretty far removed from that. And there's a lot of unpleasant consequences from this. One of which being that it sticks vendors on old kernels. Because if you've got your devices, you've got your nice 3.18 kernel, and you've got 3 million lines of code that you've written for this particular kernel, and then somebody says, well, we want you to move forward to something a little bit more modern, you have to forward port those 3 million lines of code. And that's a cost. And it's a time sink, and that's not something that consumer electronics businesses tend to look at in a very friendly sort of way. But the fact that we can't run mainline kernels on, for example, Android devices has a lot of costs in its own right. We lock out the hobbyists who do a lot of interesting stuff, and some of the dynamics that BDL was talking about just before, and the whole barrier to entry thing is there because we're losing a source of contributors there. We can't update them, so as soon as a manufacturer stops supporting a particular device, which is generally done in somewhere about 3.5 to 3.7 milliseconds after they stop selling it, you're stuck, right? You can only update that to a more secure kernel or a more functional kernel with a great deal of effort, if you can do it at all. And this is not a good thing. And there's just a whole lot of wasted effort that goes into maintaining all of this stuff. The good news is that there are actually some signs of progress here. A lot of this stuff I actually learned at the Linux Plumbers Conference a couple of months ago. I was kind of surprised to hear it. The Android Oreo release actually mandated a kernel version. I think it's the first time they did this at all. And they mandated in particular that you use one of the long-term stable kernel releases. So this was an effort to bring these manufacturers, first of all, to at least a somewhat more current kernel. I mean, 3.18 wasn't all that current even then. But it's a step in the right direction. And to minimize the fragmentation by getting them on specific kernel versions. So this is a good thing. This is a step in the right direction. But the Pi release took this further by mandating not only specific kernel versions, dropping 3.18 while they were at it, but a specific minor release version as well. They're now mandating that you have a certain level of stable updates in the kernels that you ship on your devices. So it's pushing all the manufacturers towards something a bit more current and a bit more closer to the mainline in this regard. So again, this is a good step forward. And one interesting thing that I heard in the talk where I learned this is that in all this time, they've really only had one stable related regression that has caused pain, which is why 4.4 stopped at 107 because 108 broke on them. But they thought this was pretty good, for having gone through an awful lot of stable versions over the years and only had one that caused them any trouble at all so far. So that's a good sign. The future plans, not the current plans, as I understand it, is to mandate in the future that when you ship an update to a device that contains security fixes and all that, you also have to bring forward the stable release level. So that again, you'll get not just whatever particular fixes some vendor may have cherry-picked because somebody's exploiting it on their particular device, but you'll get all of the fixes and all the stuff with it. So again, this will be a good step in the right direction. But there's actually even a bit more to it than that. The Android common kernel, the kernel from which the Android systems are all built, used to have a huge pile of patches. We talked about the Android problem for years, right? That's down to about 30 patches now. And in fact, it may be about to shrink further because the 5.0 kernel is going to include the energy-aware scheduling patches that have been out there under development for many, many years. These patches enable the scheduler to understand the energy costs of any particular scheduling decision that it makes. So if it thinks, okay, should I move this process from this CPU to that one? What will that do to my energy drain? And then it can make decisions based on that to minimize the energy costs of what it does. This is the kind of thing that has driven handset or SoC manufacturers really to replace the CPU scheduler, right? To get better battery performance, better power performance. Hopefully they won't have to do that anymore. So this is gonna further reduce the delta between what is shipped in these devices and what we have in mainline. This is a good thing. It took many years to get this in there. Finally, there's a thing called the generic system image. This is an Android open source project build that has to boot on a device for that device to be considered a compliant Android device. It verifies that the manufacturer has implemented the Android platform properly. This does not currently include the kernel. The kernel is part of the platform that the vendor provides, not what is part of the generic system image. But the future plan is to move the core kernel into the generic system image. So the Android provides the core kernel, not the SoC manufacturer or the handset vendor or whoever has put this particular kernel together. And any vendor code, any out-of-tree code has to come in only as kernel modules. And one might say, well, okay, so what? It's just going to push all that stuff over to kernel modules. And some of that will certainly happen, but it's actually a fundamental change. Because once this happens, all of that code has to conform to the Linux kernel module interface. And it can only do things that kernel modules can do. You will not be replacing the CPU scheduler in this world, right? You cannot do it. There's an awful lot of other things that you can't do. This also forces all of this code to be in much more mainline ready condition. It has to come forward with stable updates. It has to exist as kernel modules, which will make it easier for them to upstream. And as these vendors figure out that their lives are easier when they do upstream stuff, and they are figuring this out, as far as I can tell, it's going to reduce this delta even further. So we're not there yet, but we may actually get there sometime before we retire, where we can run mainline kernels on at least some of our Android devices. So this is a better picture than we've seen in recent years. Things have actually been improving. And this is the result of an awful lot of behind-the-scenes work that a lot of developers have done in engaging companies and trying to educate them as to the better ways of doing things. So it's nice to see this stuff bearing some fruit. So I've got one last topic, which given the events of the last few months, I really kind of had to bring out, which has to do with conduct in the community. So some years ago, I wrote a book, a mistake I've learned not to repeat. But when the people at O'Reilly designed the covers for the Linux series of books, they did not give us puppies or owls or even penguins, right? We got a Wild West theme. And I've never talked to the person who designed it, but all these books had this theme. And I think it can only have been done on purpose, because we were kind of a Wild West sort of community. We had our own rules, we were off by ourselves, we did things our way, and we never actually solved any disputes with a duel in the town square, but it came close a couple of times. And so you saw this in a lot of ways, right? You know, we had no source code management system, and it's amazing what we were able to do considering all of that. No change tracking, no release discipline. If you think back to the days when it took 2, 3, 4 years to get a major kernel release out, and thinking about how successful would we be now if we were still doing that. You know, we didn't have that. We didn't really have our strict rules on user space regressions that we do now. And as I mentioned before, we didn't really have much in the way of testing. We didn't have a lot of stuff that you would think that we should have. We were kind of, again, out on the frontier. And we had no code of conduct either. We had no set of rules that described how it was that we thought we should be interacting with each other. And that often showed. Now, in these days, back in the 90s and all that stuff, you know, our community was quite a bit smaller. At the time of the first kernel summit, back in 2001, the bulk of the development community, at least the most productive part of it, was able to fit into a single room. All right, we had a whole lot of them there, plus a few people who perhaps weren't part of that, but they came anyway. Right, and so we had essentially a small town. We all knew each other, even if many of us met each other for the first time at this very event back then. And we were able to interact in a pretty loose and unstructured way at that time. But if you think back to this slide that I put it back at the beginning, and numbers like that, we're not a small town anymore. We're not a small community, right? And if you think in general about the sizes of these numbers here, we weren't able to do that when we were that small. And to get from there to here, we dealt with an awful lot of scalability issues. And dealing with scalability in terms of our technology, scalability in terms of the kernel, and scalability in terms of how our community works, right? And as a part of resolving these various scalability issues, we got source code management, and we got change tracking and regression rules, and all of this good sort of stuff. But as part of this comes the realization that perhaps we were turning away people from our community because of how we dealt with each other, or how we were perceived to deal with each other, which was not always quite the same thing. And at least the realization that perhaps our next scalability issue may not be technical. It may be related instead to how we react, how we deal with each other. Well, we may find out because we do now have a code of conduct. This has been, to say the least, a bit of a controversial development in the course of our community. There are a lot of people who are worried for reasons both legitimate and not. There are people who think that, there are people who don't like the source of our code of conduct. There are people who think that it will be used by people outside our community to force an agenda that is not ours. It will force us to accept code that doesn't meet our standards, or to take the fun out of kernel development, all of that sort of stuff. And all I can say is that this code was debated and adopted by the same people who built this community in the first place, and we have no intention of allowing that to happen, right? This is going to become part of our community, and we will continue to maintain our high standards and continue to make the best kernels that we can. And beyond that, if we can manage to be nicer to each other while we're doing it, it's still even going to be fun and be more fun than it was before. All that. And that is where I stop. I think I might have a moment for a question too, I'm not sure.
We have time for maybe one question.
I think maybe Mark wants to ask a question.
So I'll skip on the irony that I work at Google. I'm asking you a question about Android, but I came all the way here to learn about things. This is not a planned question, I swear. The part about the kernel modules to reduce the interface of the code that can be added is obviously a good thing, like you mentioned. How about the kernel binary-only drivers, which seem to be a good reason why, well, not a good reason, but the reason why a lot of people start running 4.4 because they can't upgrade the kernel, otherwise the binary drivers break. Is there a future to that? A better future, that is?
Well, binary, if I understand your question, binary-only modules are going to be with us for a while yet. And there's nothing in the Android changes that will forbid that. Hopefully the requirement to move forward will make them a little bit harder to be maintained as binary-only modules, and maybe we'll get the source from there. But I feel like maybe I've not understood your question.
So my understanding, I could be wrong, is that a lot of vendors are sticking with old kernels, not just because of the many patches that they have on top, like you mentioned. Some of them don't have patches, but they're stuck with a vendor hardware that I'm not going to mention, that's stuck with a Q, that has binary drivers that only work for that kernel, and then the new hardware has a new driver, but they can't move to a new kernel because that new kernel doesn't have a binary driver and the old driver doesn't work, so they're stuck with 4.4. I don't know how widespread it is, but I've heard it is an issue.
That is one of the costs of out-of-tree code in general. And hopefully the requirements to move forward that are being imposed by Google will, if nothing else, drag the binary-only drivers forward too, for supported hardware at least. And beyond that, we have to just continue to beat on the manufacturers to actually get real drivers out there.
Thank you, Jonathan.